Thanks to the organizers for giving me the chance to present a paper that we've been submitting to FJ recently. It's not quite directly related to CMB, but it's related to foregrounds, and I think that's something that we've been talking about throughout the entire week. I think it's quite important, and this is work that has been done in collaboration with Brandon Hensley and Olivier Leray, both at JPL and Caltech. So as Hans Christian said when we kicked off this conference on Monday, the name of the game is component separation. It's not noise reduction anymore, and I couldn't agree more with that statement. And there are several aspects to this component separation to foregrounds that we've been dealing with, that we've heard about throughout this conference. One obvious thing is how to disentangle the CMB and galactic dust and synchrotron emission in order to detect gravitation, to detect B-mode polarization. That is also related to de-lensing, to remove the lens D-modes in order to detect these primordial gravitational waves. And I think we'll have more interesting talks about this by Alessandro and by Kaya tomorrow and on Friday. Another thing that I've been talking about last week is the cosmic infrared background, which is also an important, cosmological probe, but also contaminant to the CMB. And lastly, and that's what I'll be talking about for the next few minutes, we should also worry about extinction for current and next generation cosmological galaxy surveys, such as DES, KIDS, LFST, and all these fantastic instruments and surveys that are coming online now. So basically, in 2 words, what is reddening? Well, it's quite simple actually. You've got your UV and optical starlight that is scattered off of dust grains. This increases the effective wavelength, leading to the reddening of your light that needs to be corrected for. So very simply speaking, the term here is EBV. So you've got extinction, the difference between extinction of the B band and the V band. And simply speaking, if you have more dust, it correlates linearly with a larger DBV value. And having large-scale maps for the reddening and thus for the extinction by the galaxy is essential for correcting observations. Okay, so there are 2 different ways to create large-scale reddening maps and to correct your cosmological galaxy survey for this reddening. The first one is a very direct approach, in which you find many sources that have a known spectrum that you can model, so you know its true intrinsic color. And then you can use the difference between the intrinsic and the observed color to estimate the reddening towards that particular site. And if you do this for very many objects, be it stars in the galaxy or extragalactic objects, you can construct a map of the reddening. However, that is quite hard to do because there are errors in the photometry and spectroscopic errors. It's not simple to model these objects and to obtain the true intrinsic colors. Also, you need to make sure for stellar data sets that the entire that the star lies behind the entire dust column. And most importantly, it's quite tough to obtain a sufficient number of samples, especially at the galactic poles, where you're conducting cosmology. So in these regions, the stellar data seem to be sparsely available. Another way to do this is the one that has been done for the past 20 years and is probably still the state of the art, and that is to use dust optical depth as a measure of dust reddening. This has been done by, most famously, by Schlegel-Finkbeiner and Davis in 1998, and it's still the most used reddening database. It just simply relates the dust optical depth that we can infer from IRAS data with some corrections by Derby, and then calibrate this to infer the reddening value. And it's a full sky, high sensitivity measurement. However, this does require a temperature correction to go from dust emission to dust column density. That is not a simple thing to do. And the temperature correction that was employed for SFD is based on Derby data, so the angular resolution here is 1 degree. Furthermore, for infrared, emission suffers from ZODI, and maybe even more importantly, from unresolved galaxies, so from the diffuse CIB signal from the large-scale structure. Well, if that doesn't motivate you to revisit dust reddening, then maybe you're a grad student or a postdoc, young postdoc, you need to think about your H index. Yeah, well, let's try to steal some of these citations, right? Okay. So what we've been looking at is H1 as a basis for reddening data. And this all is based on the hypothesis that gas and dust are well coupled in the ISM, so they linearly trace each other. So I don't have time to go into the details of the modeling process. I just want to say that we used a SFD-like analysis to convert the H1 column density to the reddening value. And this has the great advantage of being free from many of the systematics that you find in dust-based reddening maps, such as dust temperature variations, ZODI, and most importantly, extragalactic light. And this, of course, breaks down when you go to when you go closer to the galaxy, where you've got gas that is not in the neutral atomic form, but instead molecular. So we've got limited sky coverage. The H1 data that have been used for the study are the so-called high-for-pi data, H1 for the full sky. This is work that's been published earlier this year by a collaboration of radio astronomers from Bonn and from Australia, Parkes. And it merges data from the radio telescopes in Effelsberg and in Parkes, 164-meter dish respectively. And it's supposed to replace the Leiden-Argent-Harbon survey, which has been used for the past 20 or so years as a full-scale H1 survey, and it offers all the things you could think about: higher sensitivity, resolution, systematics, better sampling, etc., etc. And it's all publicly available. So we've been using this quite simple model and this underlying H1 data set to look at the relation between reddening and H1. The left-hand side shows you the reddening value in the pan-stars stellar-based reddening map as obtained by H. Lovely a few years ago. And that is as a function of H1 column density. And you see that, well, the scatter is quite big. So that is really the caveat of using stellar data. Even though they are quite promising and they do suffer from less systematics, the sensitivity is an issue, especially at the galactic poles, where we have few stars, but where we do cosmology. So instead, if we look at the SFD data, this panel here, you see that it's quite tight correlation. It scales very nice and linearly for these stellar column densities out to some 4 times 10 to the 20. If we take a look at the double log plot and increase the range here, you see that it breaks down quite significantly here. So this is really limited by the non-atomic phases in the ISM. So we've done this for this low-density sky, obtaining a map for 40% of the sky, a resolution of 16.1 arc-minute. It's been submitted to APJ a few weeks ago. Hoping to publish this, have it accepted next week or so. So it's also available for download if you want to look at it. And spend the remaining minute or two to talk a bit about the systematics. So that's something that was done in 2010 by Pete and Graves, and they looked at so-called standard cranes. So they looked at passively evolving galaxies, for which they could very accurately determine the intrinsic color, and then used these, well, sparsely distributed galaxies to generate a low-resolution correction for the SFD map. And this is shown here for the Northern Galactic Pole, where they had data from SXS available. And these are the corrections to SFD based on elliptical galaxies. And if we take a look at the same footprint in our map, this is what we see. So the large-scale structure is very nicely seen here. We've got these low-density parts you see here. So they match extremely well. We also look at the correlation coefficients, etc. And even though these corrections to SFD are based on two completely different principles, extragalactic sources and galactic H1, you find a very tight correlation between them. Okay, lastly, a word about systematics in the H1 data. So we looked at the differences to SFD as a function of galactic latitude and H1 column density to see if the denser gas closer to the disk starts to mess with our model, if we start to be biased with respect to SFD. And we do find that, as expected, the scatter increases towards the galactic disk here and towards higher column densities here. But this is still quite a low scatter, and we're still unbiased, so we're very confident in this result. Lastly, I think that's something that would be interesting for a future study. We also looked to different extensions to this model using other traces of the diffuse ISM, such as CO, H alpha, C+, and a few more things actually. And what we find was that the addition of any of these traces doesn't significantly improve our model. So we find that especially our residuals here are completely flat with respect to any of these traces. There is some stuff here from C++, but that's all Firehouse data at very coarse resolution, so we didn't really want to use that to extend our model. So I think the future work needs to combine, for dust data, stellar data, with Gaia coming now with a new data release next year, and a combination of all this could lead to a very nice revision of SFP. Okay, so this is my summary. These are my reasons to use this map. I hope it could convince you, and yeah, looking forward to the questions. Thank you.